Hello, and thank you all for joining me. Today, I will be talking about developing embedded systems in the Ada programming language. This discussion will focus on Ada's similarities and differences with the C programming language when used to develop safe and secure software. Traditionally, safety and security in software development have been primary focuses of industries such as aerospace and railway, where a software failure can be catastrophic. These industries have created guidelines and certification requirements for this software, which guarantees that every trip you take via plane or train is free from a potential software failure. The Ada programming language was created to fulfill this industry need and certification requirement. Today, we are seeing the proliferation of complex software in industries and applications where traditionally there was no software or a software failure was not an immediate issue. As the spread continues, software that was not designed for safety or security is finding its way into safety and security critical applications. During this presentation, we will discuss why the choice of programming language is essential for the outcome of the project and how the Ada programming language can cause immediate and long-term benefits for your next embedded software application. Before we jump directly into the technical discussion, I will start with a quick introduction. My name is Robert Tice, and I'm a Technical Account Manager at AdaCore. AdaCore is a leading provider of software tools for Ada, C, C++, and Simulink. The AdaCore team includes some of the original members of the Ada design effort, as well as current active members of the Ada Reporter Group, or the ARG, which guides the future design of the language. AdaCore has top-quality compiler solutions for all versions of the language, including the Ada 2012 standard, C, and C++ for many target architectures and runtimes, including ARM, Intel x86, and PowerPC. AdaCore also has active members of the DO-178 committee, which is responsible for the certification guidelines for aircraft software. Because software development can be a very complex process, AdaCore provides more than just a compiler. The product offering includes a full suite of tools, including unit test automation, code coverage analysis, powerful static analysis, code quality tools, formal proof methods, and code generation technology. AdaCore's tools are used around the globe in safety-critical projects that directly or indirectly affect our everyday lives. These projects range from military and commercial avionics, spaceflight, railroad software, air traffic management solutions, and many other industries. The Ada programming language started as a U.S. government mandate in the late 1970s to develop a programming language which could be used in safety-critical applications. The requirements focused on the needs of real-time embedded processing applications and emphasized reliability, maintainability, and efficiency. The first validated Ada implementation was the NYU Ada Ed translator, which was certified in 1983. However, in its early years, Ada compilers struggled to implement all of the features of the large, complex language. Because of this, compiler vendors typically charged high premiums for their tools, which typically were incomplete. By 1995, compiler technology had caught up with the demands of the Ada language, and compilation and runtime performance had started to become reasonable. However, the U.S. military mandate that required Ada to be used in military programs was subsequently dropped, and developers moved on to other languages like C and Java. Many users stayed with the Ada language because of the features specified in the original design requirements. The large legacy code bases that were easily readable and very easy to maintain and update, which was beneficial to many long-lived projects. And as hardware technology advanced and projects required hardware changes, developers found that Ada, being a higher-level language than its C counterpart, required less software changes during the porting process. As the language continued to progress, new markets have picked up on the benefits of Ada and have started using it in their safety-critical applications. And now, with the advancement of static analysis and formal methods technology, developers can catch bugs and potential issues during their development process instead of during costly integration periods. So how do we explain the renewed interest from the tech community in an old language? After 30 years, Ada is stable and it has the same or better performance than C or C++ in typical embedded applications. Ada includes a complete runtime with exception handling and tasking and has evolved to include object-oriented programming paradigms and programming by contract. Many projects have now seen the benefits of static analysis techniques during development. Because of Ada's verbose language constructs, the static analysis tools can better understand more about the developer's intentions and have a better idea where there may be a potential issue. And with the Ada 2012 language constructs, we can even go one step farther. By using a subset of the language, which is known as the Spark programming language, we can do complete formal proofs on code in order to guarantee complete absence of runtime errors in a static fashion. This can completely eliminate the need for unit testing. Ada Core's products include support for many popular processor architectures and operating systems that are used in the industry today, which makes it easy to get started using Ada in any new embedded product. Let's try to answer the question of, why does the programming language chosen for a project actually matter? In safety-critical or highly reliable software, the choice of language is usually between C, C++, Java, or Ada. Each language has its technical merits, and each has been used successfully in embedded applications. So first, we have to ask, what is the criteria for the choice of language? And then, as we enumerate each choice, we can ask, what is the implication for picking this language for my application? In many applications, multiple languages are chosen for various use cases based on each language's strengths. And then the entire codebase can be integrated onto a final target. A good example of this can be found on board a large aircraft. The software running the entertainment system placed in the back of each headrest has to stream media, take user input, process and output audio, and various other tasks. Java might be a good choice for this application because it is used very often for this type of application. Therefore, we can assume Java has good library support and a large community of developers that we can hire or ask questions from as we are developing our application. For this discussion, however, we are more interested in the software keeping the plane in the air, or what's called the flight management system. Would Java be a good choice for this, or would C or Ada be a better choice? Let's use the same logic we used in the last example to walk through this problem. The first question we ask is the language supported by the industry? In our flight management system, or FMS example, we should look to manufacturers of FMSs and other avionics software and see what they are doing. This will give us some indication about what kind of community of knowledgeable developers we can expect to be out there to support our development process. If we are looking at a product which will require software maintenance, we should find out if the language we are choosing will be supported by mature companies for the foreseeable future. We wouldn't want to start a project and then a few years down the development process or a year into maintenance, find out that the tools no longer exist. We have to make sure that the language is supported by the tool as well. As I mentioned earlier, software development is much more than just the compiler. We need to make sure that there are unit testing facilities, static analysis tools, and development environments around to make the development cycle more efficient. The language we choose should generate efficient code as well. This is especially important in embedded applications with real-time constraints. We don't want to miss critical messages or sensor updates just because we were waiting for the generated instructions to finish computing something that should have taken half the time. Is the language supported on the target architecture? This is important in embedded systems because typically the hardware is chosen before the software is developed. If a strange architecture is chosen for some reason, the language should have support for it. Ada, C, C++, and Java, with a few exceptions, can fulfill all of these requirements. Maybe Java is the weakest for our FMS example because it may not have the best architecture support and is probably the least efficient out of the 4 languages. We might miss data waiting for the garbage collector, for instance. Since we have more than one answer to these questions, let's look at some more criteria that may help create a differentiation. What is the primary market using the language? Java is used in millions of devices, but is typically reserved for user-friendly media-type devices like your phone or Blu-ray player. C, C++, and Ada, being compiled languages, are typically used in the lower levels of operating systems and as application code for microcontrollers and control processors. Java is defined by a private entity where C, C++, and Ada are all defined by public groups made up of industry professionals. In the case of Ada, the software developers and software managers, as well as the tool vendors, all sit on the steering committees, which means that the evolution of the language is defined by those who use it every day. This is altogether a positive construct because, as we have seen with the development of the Ada language since its inception, it allows the language to grow over time to the needs of the industry. Where Ada stands out the most here is with the next 2 questions. Can the language help write more reliable code? And can the language help write more maintainable code? Ada was designed from the start to accomplish these 2 tasks. We will see in the later slides how this was achieved with the Ada syntax. For comparison, C and C++ were designed to program quickly and creatively, whereas Ada was designed to program correctly. We can further differentiate Ada from the other languages by looking at where typical bugs are found during the development cycle. As we all know, when we find bugs early in the development process, it is usually fairly easy to fix or redesign the application if needed. When these issues are found later, it could cause a large backtrack with lots of time lost. And for software managers, time is money. So the question is, how do we minimize the cost of development? From this graph, we can see that we should minimize the amount of time spent debugging and catch as many errors earlier on in the process as we can. This is where the benefits of Ada stand out. Features such as strong typing, verbose syntax, and higher-level language constructs allow the compiler to catch potential issues before the testing process. When this is coupled with static analysis, we can further minimize the bugs found later in the process. Therefore, we can minimize the entire cost of development. We use the term front load to explain this graph. Ada developers spend more time designing their code when time is inexpensive and less time debugging their code when time is expensive. Elaborating further on the power of the Ada compiler, we can see in this graph how the responsibility of a program can be broken down. Developers using C and C++ have the greatest flexibility with their programming, but have the most responsibility to generate correct code. Ada is the exact opposite. Much of the responsibility is given to the compiler and the tools so that the developer can focus on fulfilling the design requirements they are given. With this scenario, the application will have the optimal reliability. So now the Ada language seems great. It sounds like an optimal solution for an embedded application. But how does the Ada language achieve so much? Let's start by looking at one line of code. In this example, we have some C syntax that looks like it's a C array. And we are indexing into that array using the variable I. So let's ask some questions about this line of code to see if we might have a potential error. Is the variable tab equal to null? Well, because a C array is actually just a pointer to memory, we can use the C array syntax to move about in arbitrary memory. In this example, we have no idea if the variable tab is actually pointing at memory or if it's null. And really, we have no idea if tab is actually an array or just pointing at arbitrary memory. Is I within the boundaries of tab? We have no way of knowing this either because tab is just a pointer to memory again. There's no information behind this variable that says what the size of tab should be. If tab is actually an array, do we know if the values inside tab have been initialized? We can't tell that either. Do we know anything about the values that are supposed to go inside tab? Should they be floats? Should they be integers? We have no way of knowing that either. If tab is supposed to take floats, will this arithmetic be float division or integer division? Again, we really can't tell this from this one line of code. And more importantly, the compiler will not help us here. Let's now look at the same line of code in Ada. First, is tab null? We can definitively say no, it is not null, because in Ada, an array is actually an object and not just a pointer to memory. Since tab exists as an array, we know there are actually values inside that object. Is I within the boundaries of tab? Yes, the compiler will generate runtime checks to verify that the indexing will occur safely. If I is outside of the boundaries of tab, an exception will be raised. Has tab been initialized? We don't know that just from this line of code, and the Ada compiler won't check that for us. However, a static analysis tool can be supplemented here to catch a potential uninitialized variable situation. Is tab expecting floats or integers? Since Ada is a strongly typed language, the Ada compiler will not let the developer mix types without explicit casts. This is important because now the compiler can guarantee that the arithmetic that is happening is actually an integer division. As we have seen with that one line of code, the Ada language has some fundamental differences in design principles that can help minimize potential issues. When it comes to syntax, the Ada design methodology is to be as explicit as possible. This can be seen with the array example. If the division that was being done was between floating point and integer numbers, we would have had to explicitly cast the values during the operation. This is to avoid any potential assumptions made by the developer that is inconsistent with the compiler's implementation. Ada has a similar construct to C, where it has a header and an implementation file. In Ada, this is called the specification, or the spec, and the body. The design principle behind the Ada spec file is that it should contain enough information so that developers can glean all of the necessary information about the operation of the code without having to view the actual implementation. Ada also relies on minimizing constructs that get developers into trouble. An example of this is Ada minimizes the necessity of using pointers. In C, arrays have to be passed by pointer, whereas in Ada, the compiler will pass by reference or by copy depending on what is more efficient for the platform. That's not to say that Ada does not have unsafe constructs, though. In fact, Ada has everything that C has. But in Ada, it's easier to spot something that may be a bit dubious. For instance, let's look at this two-line C example. Here we are allocating a block of memory the size of an integer and assigning its address to the variable I. Then we are incrementing the variable I. What did we just do here? Well, I no longer points to the beginning of the memory that was allocated. This paradigm looks very common to most C developers. Now let's look at the Ada equivalent. Here we create a type, which is an access to an integer. Then we create a variable I of that type and new up an integer. This is equivalent to the malloc line in the C example. The next two lines look a little bit off. We can see the word unchecked there, which tells us immediately that we are doing something that is potentially dangerous. The first unchecked conversion allows us to convert the access type to an integer so that we can do arithmetic on the type. The second unchecked conversion allows us to convert the integer back to an access type. And we can see on the last line that we are doing the arithmetic. This looks very ugly and complicated using Ada syntax. And it should be. Pointer arithmetic is very dangerous and can cause nasty bugs that are very difficult to track down. So Ada relies on the fact that if the developer is going to do something tricky, they should be making notes about it all over the implementation. A big difference between C and Ada here is that this type of logic is necessary to the C programming methodology. Whereas in Ada, there is definitely a better, safer way to accomplish the same tasks. In this slide, we can see a typical C++ example. We are creating an array and initializing the members of that array using a mix of single assignments and a loop. We can see here that a simple initialization of an array requires that the developer write some implementation code. For a code reviewer or a code maintainer, this is non-ideal because it requires that they search through the code implementation to understand something simple like an initialization. From an automated tool point of view, there is a similar concern. Static analysis tools really can't determine the difference between an initialization or a simple assignment. Now let's look at the Ada equivalent. In this one line of code, we are doing the exact same procedure as in the C++ example. We are creating an array called A, and we are initializing it to specific values. In Ada, this is called an aggregate initialization. From the reviewer or code maintainer point of view, this is a much simpler construct. Automated tools can also now tell the difference between an initialization and an assignment procedure. We discussed Ada's strong typing in an earlier slide, but we will delve more deeply into that topic now. The driving motivation for Ada's strong typing feature is to avoid combining things in expressions that should not be combined. Take, for instance, the first example on this slide. We have created two types here based on the float type. We have a type called kilometers, which will be represented as a float, and a type miles, which will also be represented as a float. We know that these types probably shouldn't be combined without proper scaling conversions. Ada helps us out here because the compiler will not let us perform the expression adding a miles type to a kilometers type. We can do a few things here to make this work though. We can explicitly cast length 1, which is of type miles, to be of type kilometers, and then we can do the expression. We know this is wrong because miles and kilometers are two different things. If a reviewer were to come along and see many of these explicit typecasts, they might be wary of those expressions. A better way to do this would be to create a function that takes a variable of type miles and returns a variable of type kilometers. This way, we can do the conversion correctly in an external function. Another interesting feature that Ada includes is the ability to specify valid ranges for a given type. Let's look at the second example on the slide. Here we are creating a new type called ratio, which will be based on a float. We are also specifying that variables of type ratio can only have values between 0 and 100. What this tells the compiler to do is to insert runtime checks to make sure that values assigned to a type ratio are not greater than 100 or less than 0. In the expression in the last line, we are dividing two integers and then casting them to type ratio. Then we are multiplying the result by 100. Let's break down this expression into parts to see where the compiler might have an issue. We are dividing two integers and casting them to type ratio. The compiler will put a check here to make sure that the result of the division is within the proper range for type ratio. This expression is valid, so we will continue. Next, we are multiplying the result by 100. The runtime check here will raise an exception because the resulting value will be out of range for type ratio. These runtime checks are particularly useful for debugging purposes or during testing phases. However, they may cause unwanted overhead in the final product. Like all Ada runtime checks, these can be disabled at compile time to minimize the generated code overhead. Array declarations are similar to the type declarations we saw in the last slide. When we specify a new type that is an array, we have to specify the indexing type, which can be any discrete type like an integer or enumeration, and the type that will be stored as an index inside the array. Let's look at the first line of code here for an example. Type SumArray is an array that will contain integers and will be indexed by integers. Type ColorArray will also be an array and will contain integers but will be indexed by type color. So what does this mean? We can continue with the example to find out. We declare a variable called R1 of type SumArray. We then give the array the starting and ending index of the array and initialize the values in the array to 666 and 777. Let's reword this statement a slightly different way so that we can understand what is going on. R1 is an array with two indexes. The first index has a label of 10 and contains the value 666. The second index in the array has the label 11 and contains the value 777. What this line shows us is that Ada array indexing is not required to start at 0 like many other languages. We can specify any continuous range of values for the index. Let's continue on to the next line to see another example. R2 is an array of type ColorArray. It starts at index red and ends at index green. Index red has a value of 0, and the rest of the array is initialized to a value of 1. We see here another example of aggregate initialization. In this example, we can see how we can index over enumerations instead of just plain integers. Because array indexing can contain any set of continuous stream of values, Ada has something called an attribute, which can be used to get the first index and last index of the array without having to know what the actual index label is. This is especially useful when forming a loop. Like we saw when specifying a range on a type, Ada can introduce runtime checks to make sure that an array is not indexed out of bounds. In the last line, we can see that we have index R1 using an index label that is outside of the proper range. The Ada compiler will insert runtime checks here and raise an index out of range exception. This is particularly useful when considering potential security applications, as this is something that is popularly exploited in malformed code. So far, we have seen how the Ada language is structured to minimize nasty runtime bugs that can cause hours of debugging or potential security vulnerabilities. We will look at one more of these features by examining Ada's parameter modes. When a code reviewer or maintainer is looking at a function declaration, it is important for that reviewer to understand how the function's parameters are being used before, after, and during the function call. In other languages, that would require the maintainer to examine the code's implementation. Ada tries to avoid this by introducing parameter modes. The accepted modes are in parameters, which are parameters that are read-only inside the function, out parameters, which are parameters that should be written to before being read from inside the function, and in-out parameters, which are variables which can be modified inside the function. Let's look at the first example here to understand what this means. The procedure listed, called doSomething, will take three parameters. The first, called P1, is an in parameter. That means that inside this procedure we cannot assign a value to that parameter. The second parameter is an out parameter, which means that we have to assign a value to P2 before we can read a value from it inside the function. The third parameter is an in-out parameter. If C used parameter modes, all parameters would be considered in-out parameters. Why do we want this feature though? All of these checks are done at compile time, which reduces the probability that a developer will use an uninitialized parameter or misuse a parameter inside a function body. Another neat feature about the Ada compiler is that it will decide how to pass the parameter such that it is most efficient for the architecture that it is compiling for. In C++, the developer has to explicitly tell the compiler whether to pass a parameter by reference or by copy. This can mean that code that is efficient on one architecture is not efficient on another. Leaving it up to the compiler is safer and ensures that there is a better cross-platform efficiency. And unlike C, Ada can pass parameters by reference, which minimizes the usage of pointers inside the application. Let's look at the last example on the slide to understand what this means. Here we are passing some huge structure into a procedure. In C, this would be done by pointer. In Ada, the compiler will decide how this should be done. If the structure is sufficiently large, it will probably be passed by reference. A new feature of Ada that was introduced in the Ada 2012 release of the language is the idea of programming by contract. What this means is that we can specify the implementation expectations and obligations of a subprogram in the specifications of the code. Let's look at the first example on the slide to get an idea of what this means. The name of the procedure here does not give us much indication of what it is supposed to accomplish during its execution. We can see that it takes an in-out parameter, so we can guess that we will be modifying the parameter somehow. We can get a much better idea of what this procedure is supposed to do by looking at the pre- and post conditions specified here. The precondition says that the parameter v has to be greater than or equal to 10 when the procedure is called. This check gets inserted by the compiler at runtime. The post condition says that the parameter v should be different when the procedure exits than when the procedure is called. This verifies to us that the procedure p does modify the in-out parameter. If we were writing this procedure, we could be much more detailed with the contracts in order to make the spec more descriptive. Another type of contract can be applied to types. This is similar to the ranges we saw on types earlier, but more complex and more general. An invariant can be applied to an object which can check boundary constraints for encapsulated types. And a subtype predicate can capture generalized constraints on an object in order to verify its state. In the example at the bottom of the slide, we can see that we are creating a type called even with a range of 1 to 10. The predicate that we are applying here states that a variable of type even modulo 2 should be equal to 0. This means that the value stored in a variable of type even is an even number. Like most things we have discussed today, Ada inserts these checks so that the types can be verified at runtime. All of these features are great for application programming, but how does this help us create embedded code? Because Ada was originally designed to target embedded processors, it has a feature which allows developers to directly map memory onto explicit types. In this example, we are creating a record, which is similar to a C struct. This contains heterogeneous data types. We have two variables inside the record. The first is a variable of type size t, which we can see is defined here, and we have a variable of type Boolean. If we were to map this onto memory, how do we know what size and what orientation these types are in? In C, you can use compiler-specific pragmas to try to map these types, but this is compiler implementation specific. In Ada, this is done using a representation specification, or repspec. Under the record declaration, we can see a line that says for header use record. Here we are putting the variable size at byte 0 using the bits 0 to 10. The variable has next is at the next byte and is using the 6th bit inside that byte. The compiler will guarantee this memory layout and its consistency by looking for overlapping types at compile time. At runtime, it will insert all of the necessary masking and bit shifting in order to actually manipulate and access specific bytes and specific bits. For embedded bare metal work, this is incredibly useful because many mistakes happen when developers are using many bit shifts and logical statements to access sets of bits. But why is any of this useful to us as embedded developers? As we have seen through the examples, Ada is a verbose language and includes more detail about the intention of the code than its C or C++ counterparts. This contributes to Ada's readability factor. The more information that is brought out of the implementation, the easier it is for code reviewers and code maintainers to get a better understanding of what the code should be doing. This also contributes to the code's testability and readiness for static analysis tools and formal methods analysis. The runtime checks that are put in are markers that testing tools and static analysis tools can use to determine the correctness of the code. Even if those checks are turned off for production deliveries, they can contribute greatly to minimize the time code spends in testing. Adacore offers Ada compilers for various target architectures and operating systems under the GNAT Pro product line. This tool suite includes the Ada compilers as well as integrated development environments, code quality metrics tools, documentation generators, and other useful features to aid in everyday development. Adacore also offers C and C++ compilers and tools as well to complete the GNAT Pro product offering. With a tool subscription from Adacore, developers receive access to the tools, but also have direct access to our top-of-the-industry support system, which allows users to submit questions and support tickets directly to the engineers who are working on the tools. For applications where safety and security is critical, the Ada language subset called Spark is the perfect solution. Adacore offers the Spark Pro tool suite, which includes the Spark provers as well as an integrated development environment. With Spark, developers can guarantee complete absence of runtime errors without having to write a single unit test. I mentioned earlier in the slides that Ada is a perfect candidate for advanced static analysis techniques. Adacore offers the CodePeer tool to detect and assess potential runtime and logic errors before a program executes. By mathematically analyzing every line of software, this tool can help analyze existing code for potential safety issues and even detect potential security vulnerabilities. And for those users who are interested in modeling techniques, Adacore offers a tool called QGen, which is a qualifiable and tunable code generation and model verification tool for a safe subset of the Simulink and Stateflow tool suites. Using QGen in your control applications can reduce the development and verification costs for safety-critical applications through qualifiable code generation, model verification, and tight integration with Adacore's qualifiable target emulations and structural code coverage tools. Thank you for joining me today. If anyone has any questions about Ada or any of Adacore's products, don't hesitate to visit our website or send us an email at info@adacore.com. Thank you.